Thank you for clicking on this video. Please like, subscribe, and hit the bell notification for more soft, relaxing documentaries about history, science, nature, and the mysteries of our world. Perfect for learning, dreaming, and letting go. This will help the channel grow, and I would be most grateful. Now let's start the journey. In the quiet vastness of space where starlight takes millennia to reach us, there exist places so strange that they challenge everything we thought we knew about reality itself. These are the black holes, cosmic enigmas that have captivated humanity's imagination for generations. Tonight, as you settle into comfort, let us drift together through the darkness and discover what lies at the edge of forever. Our story begins not with darkness, but with light, specifically with a star. You see, most black holes are born from the death of massive stars, those brilliant giants that burn perhaps 20 times more massive than our own sun. For millions of years, these stellar titans wage a constant battle, their enormous gravity trying to crush them inward, while the intense heat and pressure from nuclear fusion in their cores pushes outward. It's a delicate balance, a cosmic dance that sustains the star's life. But eventually, inevitably, every star runs out of fuel. When one of these massive stars exhausts its nuclear reserves, something extraordinary happens. Without the outward pressure to resist gravity's pull, the star's core collapses in on itself in less than a second, an implosion so violent and so complete that it creates one of the most extreme environments in the universe. This catastrophic event, which we call a supernova, briefly outshines entire galaxies, sending shock waves rippling through space. And in the aftermath, if the original star was massive enough, what remains is something that refuses to be anything at all in the conventional sense, a black hole. The term black hole itself is relatively recent, coined by physicist John Wheeler in 1967 during a lecture. Before that, these objects were referred to by the more cumbersome phrase, gravitationally completely collapsed objects. Wheeler's simple, evocative name captured something essential. These are not merely dark, they are voids, absences, places where the normal rules seem to stop applying altogether. What makes a black hole truly a black hole is something called the event horizon, an invisible boundary in space that marks the point of no return. The event horizon isn't a physical surface you could touch. Rather, it's the spherical boundary where the escape velocity equals the speed of light. Think of it this way. On Earth, if you throw a ball upward, it needs to travel at about 7 miles per second to escape our planet's gravity entirely. Near a black hole, that escape velocity climbs higher and higher the closer you get, until at the event horizon, even light itself, traveling at 186,000 miles per second, cannot break free. This is why black holes appear black. They emit no light because no light can escape from beyond that threshold. The size of this event horizon depends entirely on the black hole's mass, and it's described by what scientists call the Schwarzschild radius. For a black hole with the mass of our Sun, this radius would be just about 3 kilometers. Imagine all that stellar mass compressed into a sphere you could walk across in less than an hour. But black holes come in many sizes, and some of the supermassive black holes at the centers of galaxies have event horizons larger than our entire solar system. Now here's where things become truly surreal. Inside the event horizon, all paths lead inward. Once you cross that boundary, you're not simply trapped by strong gravity that you lack the power to overcome. No, the very geometry of space-time itself has been so warped that every direction you could possibly travel points toward the center. Forward is toward the singularity. Backward is toward the singularity. Up, down, left, right. All roads lead to the same destination. Time and space themselves become twisted in ways that defy our everyday intuition. At the very heart of a black hole lies what we call the singularity, a point where all the black hole's mass is theoretically compressed into infinite density and zero volume. Here, the known laws of physics break down entirely. Our current equations, which work so beautifully everywhere else in the cosmos, produce infinities and impossibilities when we try to describe what happens at this central point. The singularity remains one of the greatest mysteries in all of physics, a place where Einstein's general relativity and quantum mechanics, our two most fundamental theories, cannot seem to work together. But perhaps the most mind-bending aspect of black holes is how they warp time itself. According to Einstein's theory of relativity, gravity doesn't just pull on objects, it bends the fabric of spacetime. Near a black hole, this effect becomes extreme. If you could somehow hover just outside the event horizon of a black hole and look out at the universe, you would see time in the distant cosmos rushing forward at an accelerated pace. Stars would live and die in what seemed like moments. Meanwhile, to an observer watching you from a safe distance, you would appear to move in increasingly slow motion, your image freezing at the event horizon as if time itself had stopped. In a sense, from the outside universe's perspective, nothing ever quite crosses the event horizon. It simply appears to slow down eternally, frozen at the threshold. Yet despite this apparent freezing from an outside perspective, to someone falling toward a black hole, time would feel perfectly normal. You would cross the event horizon in what seemed like an ordinary moment, unaware that to the rest of the universe, eons might be passing. This strange duality, where different observers experience time so radically differently, is one of the profound truths that black holes reveal about the nature of reality itself. As we drift deeper into understanding these cosmic mysteries, it's worth knowing that black holes aren't simply theoretical constructs dreamed up by physicists. We have actually detected them, heard them, and in recent years even seen one. The first direct detection came in 2015, when the LIGO Observatory recorded gravitational waves, ripples in the fabric of space-time itself, produced by two black holes spiraling into each other over 1 billion light-years away. These black holes, each about 30 times the mass of our Sun, circled each other with increasing speed until they merged in a violent collision that released more energy in a fraction of a second than all the stars in the observable universe combined. The space-time ripples from this ancient cataclysm washed over Earth, compressing and stretching our detectors by distances smaller than a proton. It was, in essence, the universe ringing like a bell, and we had finally built instruments sensitive enough to hear it. Then, in 2019, humanity achieved something once thought impossible. We captured an actual image of a black hole. The Event Horizon Telescope, a network of radio telescopes spread across the globe, working together as a single Earth-sized instrument, focused on the supermassive black hole at the center of the galaxy M87, some 55 million light-years away. What emerged from the data was an image both alien and strangely beautiful. A bright orange ring of superheated gas surrounding a dark shadow. That shadow, larger than our entire solar system, was the silhouette of the event horizon itself, backlit by matter being torn apart as it spiraled toward oblivion. For the first time, we weren't just detecting black holes indirectly or mathematically predicting them, we were looking at one. These images revealed something else remarkable. Black holes are surrounded by accretion disks, vast spiraling structures of gas, dust, and sometimes entire stars being gradually consumed. As this matter falls toward the event horizon, it accelerates to nearly the speed of light, and the intense friction heats it to millions of degrees, causing it to emit brilliant radiation across the spectrum, from radio waves to X-rays. Paradoxically, the region around a black hole can be one of the brightest objects in the universe, even though the black hole itself emits nothing. These accretion disks can extend for millions of miles, glowing with an intensity that can outshine all the stars in their host galaxy combined. Now, not all black holes are created equal. Astronomers have identified several distinct categories based on mass. The stellar mass black holes, born from collapsing stars, typically range from about 5 to several dozen times the mass of our Sun. Then there are intermediate mass black holes, weighing in at hundreds to thousands of solar masses. These remain somewhat mysterious, and scientists are still debating exactly how they form. But the true giants are the supermassive black holes that lurk at the centers of most large galaxies, including our own Milky Way. These behemoths can contain millions or even billions of times the Sun's mass, and their origins remain one of astronomy's great puzzles. Did they grow gradually by consuming matter over billions of years, or did they form through some more exotic process in the early universe? Our own galaxy harbors one of these supermassive black holes at its heart, located in the region we call Sagittarius A star. This cosmic giant weighs about 4 million times as much as our Sun, yet sits relatively quiet compared to the more active black holes in other galaxies. Sagittarius A star is approximately 26,000 light-years from Earth, close enough on cosmic scales for us to study its effects on nearby stars. Astronomers have tracked individual stars orbiting this invisible gravitational anchor, watching them whip around it at speeds reaching thousands of miles per second. One star, designated S2, completes an entire orbit around Sagittarius A star in just 16 years, an orbit so elliptical that the star passes within just 17 light hours of the event horizon, close enough to feel relativistic effects. Despite their fearsome reputation, black holes don't actually suck everything around them like cosmic vacuum cleaners. Their gravitational pull, while extreme near the event horizon, follows the same rules as any other massive object at a distance. If our Sun was suddenly replaced by a black hole of equal mass, which, thankfully, could never actually happen, Earth would continue orbiting exactly as it does now. We'd freeze in the darkness, certainly, but we wouldn't be pulled in. The danger comes only when you venture too close, crossing into the region where gravity becomes overwhelming. But venture too close, and you'd encounter one of the most peculiarly named and genuinely unsettling effects in astrophysics: spaghettification. This technical term describes what happens when the gravitational gradient, the difference in gravitational pull between one point and another, becomes extreme. Imagine falling feet first toward a black hole. Your feet, being slightly closer to the black hole than your head, would experience stronger gravity. At first, this difference would be subtle, but as you fell closer, the gradient would intensify. Eventually, the pull on your feet would become so much stronger than the pull on your head that you'd be stretched vertically while simultaneously being compressed horizontally. Your body would be drawn out longer and thinner, like pasta dough through a press, until you were torn apart at the molecular, then atomic, then subatomic level. For smaller black holes, this might happen well before you reach the event horizon. For supermassive black holes, with their gentler gravitational gradients, you might actually cross the event horizon intact, only to be spaghettified later as you approached the singularity. The universe, it seems, has a sense of irony, or perhaps just a brutal honesty about the extremes of existence. As you rest here in the safety of this moment, these cosmic engines of destruction continue their ancient work, reshaping the cosmos in ways both terrible and magnificent. As we continue our journey through the darkness, let us consider something that seems contradictory at first. Black holes, despite being the universe's ultimate consumers, might actually be creators as well. In the 1970s, the brilliant physicist Stephen Hawking proposed something revolutionary: that black holes aren't entirely black after all. Through a quantum mechanical process now known as Hawking radiation, black holes can actually emit particles and slowly lose mass over time. The mechanism is subtle and strange. Near the event horizon, the violent fluctuations of quantum fields can create pairs of particles and antiparticles. Normally, these pairs would immediately annihilate each other, but at the event horizon, one particle might fall into the black hole while the other escapes. To an outside observer, it appears as though the black hole is radiating particles. Over unimaginable spans of time, far longer than the current age of the universe, this process would cause a black hole to evaporate completely, ending its existence in a final burst of radiation. This revelation had profound implications. It meant that black holes have a temperature, however tiny. A stellar mass black hole has a temperature of just a few millionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that permeates space. But here's the peculiar part. The smaller a black hole becomes, the hotter it gets. As it loses mass through Hawking radiation, its temperature increases, causing it to radiate faster, which makes it smaller still, which makes it hotter, a runaway process that would end in a spectacular explosion. Of course, for black holes formed from stars, this process is so extraordinarily slow that they would take approximately 10 to the power of 67 years to evaporate, a number so vast that it makes the current 13.8 billion year age of the universe seem like the blink of an eye. Now you might wonder, if light cannot escape a black hole, how do we find them at all? The answer lies in their gravitational influence on everything around them. When a black hole has a companion star in a binary system, it can pull matter from that star in long spiraling streams. This stolen material forms the accretion disk we mentioned earlier, heating up and emitting intense X-rays before crossing the point of no return. X-ray telescopes in space can detect these brilliant beacons, and by studying the motion of the companion star, how it wobbles and orbits around an invisible partner, astronomers can calculate the mass of the hidden object. When that mass exceeds about 3 times the mass of our Sun, and no light is detected from it directly, we can be confident we've found a black hole. Black holes also reveal themselves through a phenomenon called gravitational lensing. Because they warp space-time so dramatically, they bend the path of light that passes near them, acting like cosmic magnifying glasses. If a black hole passes between us and a distant star, the star's light will bend around the black hole, sometimes creating multiple distorted images or a characteristic brightening pattern. This effect, predicted by Einstein's general relativity, has been used to detect isolated black holes drifting through the galaxy, objects that would otherwise be completely invisible to us. The relationship between black holes and galaxies runs deeper than we once imagined. Astronomers have discovered that there's a remarkably tight correlation between the mass of a galaxy's central supermassive black hole and properties of the galaxy itself, particularly the velocity dispersion of stars in its central bulge. A galaxy with faster moving stars in its core invariably hosts a more massive black hole. This relationship suggests that black holes and their galaxies grow together, influencing each other's evolution through cosmic history. When galaxies merge, a violent process that takes hundreds of millions of years, their central black holes eventually sink toward the center of the new combined galaxy, where they orbit each other before ultimately colliding and merging themselves. These galactic mergers can create something truly spectacular, a quasar. Quasars are among the most luminous objects in the universe, powered by supermassive black holes actively devouring enormous amounts of matter. During the universe's youth, quasars were far more common, shining with the light of trillions of suns as gas-rich galaxies collided and funneled material into their central black holes. The energy released by this feeding frenzy was so intense that it could literally blow gas out of the galaxy, potentially regulating or even halting star formation. In this way, black holes act as cosmic thermostats, controlling the growth of their host galaxies. Today, most supermassive black holes, including our own Sagittarius A star, are relatively quiet, sipping rather than gorging on the meager material available to them. Yet even in their quieter moments, black holes can produce extraordinary phenomena. Some black holes launch jets, narrow beams of particles and radiation that stream away from the poles at nearly the speed of light, extending for thousands or even millions of light years into space. These jets are powered by a combination of the black hole's rotation and powerful magnetic fields threading through the accretion disk. The exact mechanism is still not fully understood, but the result is spectacular. Twin searchlights piercing the cosmos, occasionally pointed directly at Earth, where we observe them as blazars, objects of such intense variability and energy that they puzzled astronomers for decades. Perhaps one of the most intriguing possibilities is that black holes might serve as laboratories for testing the very limits of physics. The extreme conditions near a black hole, where gravity is strongest, space-time is most warped, and quantum effects might become important, could reveal phenomena we've never encountered. Some theorists speculate about exotic possibilities: white holes that spew matter out rather than consuming it, wormholes that connect distant regions of space-time, or even firewalls of intense radiation at the event horizon. While these ideas remain highly speculative and debated, they remind us that black holes continue to challenge our understanding, existing at the boundary between what we know and what we can only imagine. As you breathe slowly in and out, consider how these objects, born from stars that lived and died billions of years ago, continue to shape the cosmos. They are the universe's sculptors and destroyers, its deepest mysteries and its most extreme laboratories, all wrapped into regions of space where infinity becomes almost tangible. In the gentle silence of contemplation, let us explore one of the strangest consequences of black holes: the information paradox. This puzzle has vexed physicists for decades, creating a tension between two of our most fundamental theories. According to quantum mechanics, information can never be truly destroyed. The state of any system should, in principle, be recoverable from its future state. Yet when something falls into a black hole and crosses the event horizon, that information seems to vanish from the universe forever. And if the black hole eventually evaporates through Hawking radiation, where does that information go? Does it disappear, violating quantum mechanics? Is it somehow encoded in the radiation, or does it remain trapped at the event horizon in ways we don't yet understand? Stephen Hawking himself struggled with this paradox for much of his life, eventually proposing that information might be preserved in subtle correlations within the Hawking radiation, though the debate continues to this day, with physicists exploring exotic ideas like holography and quantum entanglement to resolve this cosmic mystery. This information paradox connects to another profound idea, the holographic principle. Some physicists propose that all the information contained within a volume of space, including everything that falls into a black hole, might actually be encoded on its boundary, like a three-dimensional image projected from a two-dimensional surface. For a black hole, this boundary would be the event horizon itself. In this view, the entropy or disorder of a black hole is proportional not to its volume, but to the surface area of its event horizon. This discovery, made by physicist Jacob Bekenstein and refined by Hawking, was startling. It suggested that our three-dimensional reality might, in some deep sense, be a projection from information stored on a distant two-dimensional surface. The implications stretch far beyond black holes, potentially applying to the entire universe itself. Now, while we've spoken of stellar mass and supermassive black holes, there's a theoretical possibility that sends shivers through the imagination: primordial black holes. These hypothetical objects would have formed not from collapsing stars, but in the first fractions of a second after the Big Bang, when the universe was unimaginably dense and hot. Tiny fluctuations in density during this primordial chaos could have created black holes of any mass, from less than the mass of a mountain to thousands of times the Sun's mass. If they exist, primordial black holes could help explain several cosmic mysteries, including possibly accounting for some or all of the dark matter that makes up most of the mass in the universe. Some primordial black holes might be small enough that they would have already evaporated through Hawking radiation, while others could be silently drifting through the galaxy at this very moment, detectable only through their gravitational effects. The question of what lies beyond the event horizon has inspired not just scientific inquiry, but philosophical wonder. Once you cross that threshold, the future becomes unavoidable. You will reach the singularity no matter what you do. But here's something remarkable. The exact nature of what you'd experience remains uncertain. Some solutions to Einstein's equations suggest that the interior of certain rotating black holes might contain truly bizarre structures. A rotating black hole, described by the Kerr metric, has not one but two event horizons, and between them lies a region called the ergosphere. In the ergosphere, spacetime itself is dragged around the black hole, a phenomenon called frame dragging. An object in this region cannot remain stationary, it must rotate with the black hole, carried along by the twisting of space itself. This rotation could theoretically be used to extract energy from the black hole through a process called the Penrose process, where particles entering the ergosphere could split, with one falling in and the other escaping with more energy than it entered with. But the strangeness doesn't end there. Some theoretical models suggest that inside a rotating black hole, you might encounter what's called an inner horizon, beyond which the singularity isn't a point, but a ring. This ring singularity would have a truly mind-bending property. It might contain a passage to another region of space-time entirely, either another part of our universe or potentially another universe altogether. These are the famous wormholes of science fiction, though in reality, such passages would likely be violently unstable and utterly lethal to anything trying to traverse them. Still, the mathematics allows for these possibilities, reminding us that black holes remain frontiers where our knowledge gives way to speculation. The fastest spinning black holes we've observed rotate at truly staggering speeds. The supermassive black hole in the galaxy NGC 1365 spins at nearly 84% of the maximum rate allowed by physics. If it spun any faster, it would exceed the speed of light at its event horizon, which relativity forbids. At such extreme rotation rates, the frame dragging effects become tremendously powerful, and the ergosphere swells to encompass a large region around the black hole. This spin is thought to be the key ingredient in launching those spectacular jets we mentioned earlier, with the rotational energy somehow tapped by magnetic fields to accelerate particles to relativistic speeds. When we observe the centers of distant galaxies, we sometimes witness black holes in the act of feeding, episodes called active galactic nuclei, or AGN. During these feeding events, which can last for millions of years, the black hole's accretion disk blazes with such intensity that it can be detected across billions of light years. The radiation pressure from this feeding frenzy is so intense that it creates powerful winds of ionized gas, blowing outward at thousands of kilometers per second. These winds can span the entire galaxy, pushing gas away and potentially shutting down star formation across vast regions of space. In this way, supermassive black holes don't just passively sit at galactic centers, they actively regulate the life cycles of galaxies themselves, determining how many stars can form and when galactic growth must cease. And here's something that brings our journey back to Earth, in a sense. The detection of gravitational waves from merging black holes hasn't just confirmed Einstein's century-old prediction, it's opened an entirely new way of observing the universe. Before LIGO, astronomy relied entirely on electromagnetic radiation, visible light, radio waves, X-rays, and so on. But gravitational waves are fundamentally different. They're ripples in space-time itself, carrying information that light cannot. This means we can now detect events that produce no light at all, like the merger of two black holes in empty space, far from any stars or gas. Since that first detection in 2015, LIGO and its partner observatories have detected dozens of black hole mergers, revealing a population of these objects we never knew existed and teaching us about the extreme physics of space-time in its most violent moments. Rest now in the knowledge that across the universe, in the depths of space where no light reaches, these cosmic phenomena continue their eternal dance, merging, spinning, consuming, and perhaps in ways we're only beginning to understand, creating as well. As we drift deeper into the night, let us consider the very fabric of reality around these cosmic enigmas. When Einstein first developed his theory of general relativity in 1915, he himself was skeptical about black holes. The equations predicted them, solutions found by Carl Schwarzschild just months after Einstein published his theory. But Einstein found the idea so extreme that he wrote papers arguing they couldn't exist in nature. He believed something would always prevent such complete gravitational collapse. It's one of history's beautiful ironies that Einstein's most revolutionary theory predicted objects so strange that even he couldn't accept them. Yet, today we've confirmed they're among the most common endpoints of stellar evolution. Sometimes nature is more imaginative than even our greatest minds dare to be. The journey to accepting black holes took decades, and one crucial step came from a young physicist named Subrahmanyan Chandrasekhar. In 1930, while still in his early 20s and traveling by ship from India to England, Chandrasekhar calculated what would happen to stars after they died. He discovered that there's a limit, now called the Chandrasekhar limit, of about 1.4 solar masses. A dead star's core more massive than this cannot be supported by electron degeneracy pressure, the quantum mechanical effect that holds up white dwarfs. If the core exceeds this limit, it must collapse further, either into a neutron star or, if massive enough, into a black hole. This work, which would eventually earn him the Nobel Prize, provided the theoretical foundation for understanding that black holes weren't just mathematical curiosities, they were inevitable consequences of how massive stars die. Now imagine this: there may be millions of black holes wandering through our galaxy alone. Most stellar mass black holes aren't conveniently located in binary systems where we can easily detect them by watching them feed on a companion star. Instead, they drift silently through the darkness, invisible and isolated, detectable only when they happen to pass in front of background stars, briefly magnifying their light through gravitational lensing. Astronomers estimate that the Milky Way contains somewhere between 100 million to 1 billion stellar mass black holes, remnants of massive stars that lived and died over our galaxy's 10 billion year history. The vast majority remain completely unknown to us, dark wanderers moving through the space between stars. But what about the possibility of truly tiny black holes? In theory, if you could compress any amount of mass into a small enough space, a volume smaller than its Schwarzschild radius, you'd create a black hole. For Earth, that would mean crushing our entire planet into a sphere less than 2 centimeters across, about the size of a marble. For a human being, you'd need to compress all your mass into a region smaller than an atom. These are clearly impossible with any known natural process, but they illustrate an important principle. It's not about how much mass you have, but how densely you can pack it. This is why black holes can only form from incredibly extreme events. There are very few circumstances in nature that can compress matter to such extraordinary densities. The centers of galaxies may harbor an even stranger possibility: binary supermassive black holes, two cosmic titans orbiting each other in the aftermath of a galactic merger. As galaxies collide and combine, a process happening constantly throughout the universe, their central black holes are drawn together by gravity and friction with surrounding gas and stars. But getting them to actually merge is surprisingly difficult. Once they're orbiting each other closely, they can become stuck in what's called the final parsec problem. At separations of about 1 parsec, or roughly 3 light-years, there may not be enough nearby matter to carry away the orbital energy needed for the black holes to spiral closer together. They could potentially orbit each other for billions of years before finally merging. However, when they do eventually collide, the gravitational wave signal would be stupendous, far more powerful than anything LIGO can detect, requiring space-based detectors to observe. These mergers would produce something remarkable: a single, larger black hole that's initially violently distorted, oscillating and ringing like a struck bell as it settles into its final, stable form. The gravitational waves emitted during this ring-down phase carry a unique signature that tells us about the final black hole's mass and spin, like how the tone of a bell tells you about its size and shape. By studying these ring-down signals, physicists can actually test whether general relativity holds true even in these most extreme conditions, or whether new physics emerges when gravity becomes so intense. Here's something that challenges our intuition even further. Time dilation near black holes doesn't just slow time, it creates scenarios that seem paradoxical. Imagine twins, one who stays on Earth and one who travels to orbit close to a black hole's event horizon for what feels to them like 1 year, then returns home. Due to the extreme time dilation, the twin who stayed behind might have aged decades or even centuries. This isn't science fiction speculation, it's a direct consequence of general relativity that we've confirmed through precise measurements with atomic clocks at different altitudes on Earth, though the effects near a black hole would be vastly more extreme. Near the event horizon of a supermassive black hole, 1 hour experienced by someone in close orbit could correspond to years or even decades passing in the distant universe. You could, in theory, use a black hole as a one-way time machine to the future, though the return journey would be impossible. The universe may also contain stellar black holes paired with other stellar black holes in binary systems, slowly spiraling toward each other over millions or billions of years. These systems are cosmic timers, gradually losing energy through the emission of gravitational waves, ripples so faint that they're essentially undetectable until the final moments before merger. For most of their lives, these binary black holes orbit each other in relative serenity, perhaps survivors of a binary star system where both stars went supernova. But in the final minutes before they collide, everything accelerates. The black holes spiral inward faster and faster, orbiting each other hundreds of times per second in the final instant, releasing more energy in gravitational waves than all the stars in the observable universe emit in light. Then in a fraction of a second, they merge and silence returns, a silence disturbed only by the faint ring-down of the newborn black settling into equilibrium. Let your mind rest on this. Throughout the cosmos at this very moment, ancient binary systems are spiraling closer. Quasars are blazing across billions of light years, and silent black holes drift through the darkness between stars. The universe's greatest extremes unfold in the quiet of space, indifferent to observers, following laws we've only recently begun to comprehend. In the stillness of this moment, let us turn our attention to some of the most peculiar predictions about black holes, ideas that stretch even further into the realm of the extraordinary. One such concept involves charged black holes described by what physicists call the Reissner-Nordström solution. While most black holes in nature are thought to be electrically neutral, any charge would quickly be neutralized by attracting opposite charges from surrounding space, the theoretical possibility of a charged black hole reveals fascinating structure. A charged black hole would have two event horizons, an outer and an inner one, and the region between them would possess properties unlike anywhere else in the cosmos. But nature, it seems, prefers its black holes neutral, as the electromagnetic forces would work quickly to discharge any significant electrical imbalance. The relationship between black holes and the arrow of time presents another deep mystery. The second law of thermodynamics tells us that entropy, disorder, always increases in a closed system, giving time its forward direction. When Bekenstein and Hawking discovered that black holes have entropy proportional to their surface area, they revealed something profound. Black holes are the most efficient entropy containers in the universe. A black hole has more entropy than any other object of the same mass could possibly have. This means that when matter falls into a black hole, the universe's total entropy increases dramatically, and the arrow of time becomes even more firmly pointed in one direction. In a sense, black holes are the ultimate embodiments of irreversibility. They represent the point of no return, not just spatially, but thermodynamically as well. Throughout the universe, there exists a cosmic speed limit for how large a black hole can grow through accretion, through feeding on surrounding matter. This is called the Eddington limit, named after astrophysicist Arthur Eddington. As matter spirals into a black hole and heats up, it emits intense radiation. This radiation pushes outward on any additional infalling matter with tremendous force. There's a balance point where the outward radiation pressure exactly equals the inward pull of gravity, and this determines the maximum rate at which a black hole can steadily consume matter. For a black hole to grow faster, it either needs to exceed this limit temporarily during chaotic feeding events, or it needs to find ways to accrete matter more efficiently, perhaps through thick disks where radiation is trapped. This limit helps explain why even the most massive, supermassive black holes took billions of years to reach their current sizes. There are fundamental physical constraints on how quickly they can grow. Yet astronomers have discovered supermassive black holes, billions of times the Sun's mass, that existed when the universe was less than 1 billion years old, just a fraction of its current age. This presents a fascinating puzzle. How did these black holes grow so large so quickly? The universe simply wasn't old enough for them to have grown from stellar mass black holes at the Eddington limited rate. Several possibilities exist. Perhaps they formed from the direct collapse of massive gas clouds in the early universe, creating seeds that were already thousands or millions of solar masses. Or perhaps they fed at super Eddington rates during the chaotic conditions of the young cosmos, growing faster than the standard theories would predict. Or possibly they formed through exotic processes we haven't yet imagined. These ancient, massive black holes challenge our understanding of how structure formed in the early universe. The study of black holes has also revealed unexpected connections to other areas of physics. String theory, a theoretical framework attempting to unify quantum mechanics and gravity, makes specific predictions about black holes that differ subtly from classical general relativity. For instance, string theory suggests that the event horizon might be replaced by a fuzzball, a tangled ball of quantum strings without a true singularity at the center. While we can't yet test these ideas directly, black holes serve as laboratories where different theories of quantum gravity make distinct predictions. As our observations become more precise, studying the shadows of black holes, detecting subtle features in gravitational waves, or observing matter in the final moments before it crosses the event horizon, we may be able to distinguish between these competing theories. Black holes also exhibit what physicists call no-hair theorems. This somewhat whimsical name expresses a profound idea. Once a black hole forms, nearly all information about what fell into it is lost. A black hole can be completely described by just 3 properties: its mass, its electric charge, and its angular momentum, or spin. Everything else, whether it formed from hydrogen or iron, whether it consumed planets or asteroids, what elements composed the original star, all of that information vanishes behind the event horizon. As physicist John Wheeler put it, black holes have no hair, meaning they have no distinguishing features beyond these three numbers. Two black holes with identical mass, charge, and spin are fundamentally indistinguishable regardless of their histories. This simplicity is both elegant and unsettling, representing a kind of cosmic amnesia. Consider also the fate of light itself near a black hole. At a distance of precisely 1.5 times the Schwarzschild radius from the center, there exists a region called the photon sphere. At this exact distance, gravity is so strong that light can orbit the black hole in circular paths. Photons traveling at the speed of light trace endless circles around the black hole, neither falling in nor escaping. If you could somehow position yourself at this location and look to the side, you might theoretically see the back of your own head. Light from you would circle the black hole and return. Of course, this scenario is entirely hypothetical and impossible in practice, but it illustrates how profoundly black holes warp the paths of light. Just slightly closer than the photon sphere, and light spirals inexorably inward, just slightly farther, and it can escape to infinity. As we've explored black holes through gravitational wave astronomy, we've made another remarkable discovery. Some of the black holes we've detected through their mergers are more massive than we expected stellar mass black holes to be. There appears to be a gap, sometimes called the mass gap, where very few black holes exist, roughly between 2 and 5 solar masses. Below this range, we find neutron stars. Above it, we find black holes. The recent detection of objects in this mass gap has sparked debate about whether they're the most massive neutron stars, the smallest black holes, or perhaps something else entirely. Additionally, some of the black holes detected by LIGO are surprisingly massive, dozens of solar masses larger than models of stellar evolution predicted could form from single-star collapse. These might form from the mergers of smaller black holes, or they might indicate that stars in the early universe with different chemical compositions could create more massive black holes than stars today. Rest here in contemplation of these mysteries. The universe reveals itself slowly through patience and precision, offering answers that often lead to deeper questions. Black holes stand at the frontier of knowledge, where observation meets theory, where the proven touches the speculative, and where each discovery illuminates both what we know and the vastness of what we have yet to understand. As we journey deeper into this cosmic night, let us consider how black holes sculpt not just space and time, but the very evolution of galaxies across the universe. Astronomers have discovered that virtually every large galaxy hosts a supermassive black hole at its center, and this is no coincidence. The relationship is so consistent that it suggests a deep connection between the formation and growth of galaxies and their central black holes. When we look at elliptical galaxies, those vast, football-shaped collections of stars, the mass of the central black hole is typically about 0.5% of the total mass of all the stars in the galaxy's central bulge. This tight correlation, discovered through painstaking observations of stellar motions and gas dynamics, tells us that galaxies and their black holes must evolve together, each influencing the other's growth through billions of years of cosmic history. The feeding habits of supermassive black holes follow patterns that change over cosmic time. In the distant past, when the universe was young and galaxies were still forming and merging frequently, black holes fed voraciously, creating the brilliant quasars that dominated the early cosmos. Today, most supermassive black holes exist in a state of relative starvation, with only occasional meals when a gas cloud or unlucky star wanders too close. Our own Sagittarius A star is remarkably quiet, accreting matter at a rate of only about 1 Earth mass every few thousand years, barely a trickle compared to its potential appetite. But this quiescence can be interrupted. Astronomers have observed sudden brightenings from Sagittarius A star, flares of X-ray, and infrared radiation lasting for hours, likely caused by hotspots in the accretion flow or the disruption of asteroids or comets that ventured too close to the event horizon. One of the most dramatic events that can befall a star is a tidal disruption event, where the star passes close enough to a black hole to be torn apart by tidal forces. As the star is stretched and shredded, roughly half of its material is flung away into space at high velocity, while the other half falls back toward the black hole, forming a temporary accretion disk that blazes with intense radiation. These events produce spectacular flares that can briefly make a previously quiet black hole outshine its entire host galaxy. Astronomers have detected dozens of these tidal disruption events, each providing a unique laboratory for studying how matter behaves in the extreme gravitational environment near a black hole. The process is violent yet predictable, following the laws of physics with almost orchestral precision. The star approaches, is stretched, torn, scattered, and consumed, all in accordance with the equations of general relativity. Within the realm of theoretical physics, some researchers have explored the possibility of traversable wormholes, shortcuts through spacetime that might, in principle, connect distant regions of the universe or even different universes entirely. These hypothetical structures are related to black holes but would require exotic forms of matter with negative energy density to hold them open and prevent them from collapsing. While no evidence exists that such wormholes are real, and the physics required to create and maintain them appears to violate known laws, they remain a fascinating topic at the intersection of general relativity and quantum mechanics. If they existed, a traversable wormhole might appear somewhat similar to a black hole from the outside, a spherical region that distorts light. But instead of leading to a singularity, it would open into another region of spacetime. For now, these remain firmly in the realm of speculation, beautiful mathematical possibilities awaiting either confirmation or refutation by deeper understanding of quantum gravity. The ultimate fate of black holes connects to the ultimate fate of the universe itself. If the universe continues expanding forever, as current observations suggest, it will eventually reach a state called heat death, maximum entropy, where all matter has decayed and all black holes have evaporated through Hawking radiation. In this unimaginably distant future, perhaps 10 to the power of 100 years from now, even the largest supermassive black holes will have slowly radiated away their mass, leaving behind only a cold, dark, empty universe filled with nothing but the faint whisper of photons spreading ever farther apart. Black holes in this scenario would be among the last structured objects to exist, the final holdouts against the universe's inexorable slide toward maximum disorder. They would reign over an increasingly empty cosmos before they too succumb to evaporation, winking out one by one in final bursts of radiation, leaving behind only memories encoded in quantum correlations scattered across infinite space. The mathematics describing black holes contain solutions so strange that they border on the philosophical. The rotating Kerr black hole equations predict a structure called a Cauchy horizon, an inner boundary beyond which the usual rules of cause and effect might break down. Inside this region, closed time-like curves might exist, paths through space-time that loop back on themselves, theoretically allowing travel to one's own past. Of course, these solutions come with severe caveats. Most physicists believe that quantum effects or classical instabilities would prevent these regions from existing in reality, or would make them instantly lethal to anything approaching them. Still, the fact that Einstein's equations that have been tested and confirmed in countless experiments, contain these possibilities tells us something profound about the nature of space-time itself. Reality near black holes is stranger than our everyday intuition can readily grasp. Black holes also provide an unexpected tool for understanding the nature of dark matter, that mysterious substance that makes up about 27% of the universe's mass energy, but doesn't interact with light. Some theories propose that a fraction of dark matter might consist of primordial black holes formed in the early universe. These ancient black holes would be invisible like dark matter, interact only through gravity like dark matter, and could potentially explain some of the unusual observations that standard dark matter models struggle with. However, observations have largely ruled out the possibility that primordial black holes make up all or even most of dark matter. If they did, we would see more gravitational lensing events and other telltale signatures than we actually observe. Still, they might constitute a small fraction of the dark matter, adding yet another component to the universe's complex inventory. Perhaps one of the most humbling aspects of black holes is how they expose the limits of human knowledge. At the singularity, where density becomes infinite and the curvature of spacetime diverges, our equations simply break down. We cannot predict what happens there because our mathematical tools fail us. This isn't just a practical limitation, it's a fundamental signal that we're missing something important in our understanding of nature. Most physicists believe that a complete theory of quantum gravity, one that unifies general relativity and quantum mechanics, would replace the singularity with something else, perhaps a region of intense but finite curvature, or a quantum foam of space-time itself, fluctuating at the smallest scales. But until we develop and test such a theory, the singularity remains a boundary to knowledge, a place where we must admit our ignorance and accept that the universe still holds secrets we cannot yet comprehend. Close your eyes and breathe deeply. Somewhere in the darkness between stars, ancient black holes drift in silence, their histories unknown, their futures stretching toward an almost infinite expanse of time. They are the universe's deepest wells, its most extreme laboratories, and its most persistent mysteries, guardians of secrets that may take centuries more to unravel. In the quietude of space, where distances are measured in light years and timescales span eons, black holes continue their work, shaping the cosmos in ways both subtle and profound. Let us consider now the phenomenon of relativistic jets in greater detail, those extraordinary beams of particles and energy that some black holes launch into space. The particles in these jets travel at speeds exceeding 99% of the speed of light, and as they do, relativistic effects come into play. From our perspective, watching from Earth, these jets can appear to move faster than light itself, an illusion called superluminal motion. This happens because the particles are moving almost directly toward us at nearly light speed, so the light they emit at different times reaches us at nearly the same moment, compressed together. The jet appears to cover vast distances in impossibly short times, though of course nothing actually exceeds the cosmic speed limit. It's simply nature playing tricks with geometry and the finite speed of light. The power required to launch and sustain these jets is staggering. Some of the most luminous jets carry away energy equivalent to the complete annihilation of several suns' worth of matter each year. The mechanism that accelerates particles to such extreme speeds involves magnetic fields that thread through the accretion disk and tap into the rotational energy of the black hole itself. This process, called the Blandford-Znajek mechanism, after the physicists who proposed it, essentially turns the spinning black hole into a cosmic generator. The magnetic field lines, anchored in the disk and twisted by the black hole's rotation, act like enormous particle accelerators, flinging matter outward along the rotational axis. The jets can remain stable for millions of years, carving through the intergalactic medium and creating vast cavities and shock waves visible in radio observations. Black holes also exhibit fascinating behavior when they interact with magnetic fields in another way, through a process called magnetic reconnection. In the turbulent plasma of the accretion disk, magnetic field lines can become tangled and stressed. When these field lines suddenly snap and reconnect in a different configuration, they release enormous amounts of energy in a fraction of a second, heating particles and accelerating them to high speeds. These reconnection events might be responsible for some of the rapid variability we observe in black hole systems, sudden flares and eruptions that can increase the brightness by factors of hundreds or thousands in mere hours. It's a reminder that the environment around a black hole is not static or smooth, but rather a churning, chaotic realm where magnetic fields dance and energy cascades in unpredictable ways. Now, consider the incredible precision required to image a black hole, as was accomplished with M87's black hole in 2019. The Event Horizon Telescope achieved an angular resolution of about 20 micro-arc seconds. That's roughly equivalent to being able to read a newspaper in New York from Paris, or to spot an orange on the surface of the Moon from Earth. This extraordinary resolution was achieved by combining radio telescopes from around the world into a virtual telescope the size of our entire planet, using a technique called very long baseline interferometry. The data collected filled hundreds of hard drives that had to be physically transported to central processing facilities because the data volume exceeded what could be transmitted over the internet. Teams of scientists then spent months carefully calibrating and combining the signals, using sophisticated algorithms to reconstruct the image from the fragmentary data. The result, that iconic orange ring surrounding a dark shadow, represented not just a technological triumph, but a confirmation that our mathematical descriptions of these extreme objects truly reflect reality. The black hole in M87, designated M87 star, is a monster among monsters. With a mass of approximately 6.5 billion times that of our Sun, its event horizon spans a region larger than our entire solar system. The jet launched from this black hole extends for at least 5,000 light-years into space, visible as a brilliant blue streak in optical images of the galaxy. Despite its enormous size, M87 star is actually somewhat inefficient at converting the matter it consumes into radiation. It radiates at only a tiny fraction of its Eddington limit. Yet even this modest feeding produces spectacular effects, pumping energy into the surrounding galaxy and far beyond. The black hole essentially acts as a cosmic engine at the heart of M87, influencing the galaxy's structure and evolution over billions of years. When we observe black holes in X-rays, we sometimes detect a phenomenon called quasi-periodic oscillations, or QPOs, regular variations in brightness, that repeat with remarkable consistency, often hundreds of times per second. These oscillations are thought to arise from various processes in the inner accretion disk, perhaps from hotspots orbiting close to the event horizon, or from instabilities in the flow of matter, or from oscillations in the disk itself as it responds to the black hole's gravity. By studying the frequencies and patterns of these QPOs, astronomers can probe the environment just outside the event horizon, testing predictions of general relativity and mapping the space-time geometry in regions where gravity is extraordinarily strong. Each QPO is like a lighthouse beam sweeping past Earth, carrying information about conditions at the edge of the abyss. Black holes can also serve as natural particle accelerators, producing cosmic rays, high-energy particles that bombard Earth from space. When matter in the jets or accretion disk is accelerated to near light speed, some particles escape and travel through intergalactic space, eventually reaching our solar system. The most energetic cosmic rays ever detected carry energies equivalent to a well-thrown baseball, concentrated in a single subatomic particle. The sources of these ultra-high energy cosmic rays remain somewhat mysterious, but supermassive black holes with powerful jets are strong candidates. When these particles strike Earth's atmosphere, they create cascades of secondary particles that shower down to the surface, occasionally triggering detectors in cosmic ray observatories. In this way, black holes billions of light-years away can make their presence felt here on Earth, sending messengers that travel across the universe to reach us. There's a haunting beauty in how black holes connect the largest scales to the smallest. They begin with the quantum uncertainty of particle pairs at the event horizon, manifest through the relativistic warping of spacetime at intermediate scales, and influence the structure and evolution of galaxies at the grandest cosmic scales. They are bridges between different realms of physics, between gravity and quantum mechanics, between thermodynamics and information theory, between the beginning of the universe and its ultimate end. In studying black holes, we're not just learning about exotic objects in distant space, we're probing the fundamental nature of reality itself, testing the limits of our theories and glimpsing the deep unity underlying the physical laws that govern everything, from the smallest quantum fluctuations to the largest structures in the cosmos. Let yourself drift now, suspended between awareness and sleep, knowing that the universe continues its ancient rhythms. Stars are born and die, galaxies slowly wheel through space, and black holes stand as eternal monuments to the power of gravity, unchanging yet ever-changing, simple yet infinitely complex. In the deepening stillness, let us turn our attention to one of the most poignant interactions between black holes and their surroundings, the relationship between black holes and the stars that orbit them. At the center of our galaxy, astronomers have been tracking individual stars orbiting Sagittarius A star for over 2 decades now, creating a detailed map of their movements. One star in particular, called S2, has provided some of the most compelling evidence for the black hole's existence, and has even allowed us to test Einstein's predictions in the strong gravity regime. During its closest approach in 2018, S2 passed within about 17 light hours of the black hole, traveling at nearly 3% of the speed of light. At this distance and velocity, relativistic effects became measurable. Astronomers detected the gravitational redshift of the star's light, its wavelength stretched by the intense gravity, exactly as general relativity predicts. This observation represented a triumph of both theoretical physics and observational astronomy, confirming Einstein's century-old equations in one of the most extreme environments we can study. But S2 is not alone in its dangerous dance. There's an entire population of stars in the central parsec of our galaxy, living their lives under the gravitational influence of Sagittarius A star. These stars experience a very different environment than stars in the quiet suburbs of the galaxy where our Sun resides. The stellar density near the galactic center is millions of times higher than in our neighborhood, meaning close encounters between stars happen far more frequently. Some of these stars pass so close to the black hole that tidal forces noticeably distort them, stretching them slightly during each orbit. Over time, some will venture too close and be tidally disrupted, ripped apart in a violent display of gravity's power. Others might be ejected from the galaxy entirely, flung outward at escape velocity by gravitational interactions with other stars, or by a close encounter with the black hole itself. These hypervelocity stars have been detected racing through the galaxy at speeds of hundreds or even thousands of kilometers per second, carrying with them the memory of their violent encounters near the galactic center. The formation of stars near supermassive black holes presents another fascinating puzzle. The intense tidal forces and radiation environment near these black holes should make it extremely difficult for molecular clouds to collapse and form stars. Yet observations reveal young, massive stars orbiting close to Sagittarius A star, stars that can only be a few million years old, practically newborns on cosmic timescales. How did these stars form in such a hostile environment? One possibility is that they formed farther away and somehow migrated inward, though the mechanisms for such migration remain debated. Another possibility is that the gas disks surrounding the black hole can fragment under certain conditions, forming stars despite the challenging environment. These young stars near the black hole live fast and die young, burning through their nuclear fuel in just a few million years before exploding as supernova or collapsing into black holes themselves, potentially feeding their massive neighbor. Black holes also play a crucial role in a phenomenon called feedback, which helps explain why the universe doesn't contain more stars than it does. When a supermassive black hole feeds actively, the energy it releases through radiation, winds, and jets heats the surrounding gas to temperatures of millions of degrees. This hot gas cannot cool down and collapse to form stars. In massive galaxy clusters, where hundreds or thousands of galaxies congregate, the central supermassive black hole effectively acts as a thermostat, preventing runaway cooling that would otherwise lead to enormous rates of star formation. X-ray observations of galaxy clusters reveal vast cavities carved by jets from the central black hole, regions where the hot gas has been pushed aside. These cavities can be hundreds of thousands of light-years across, representing a staggering amount of energy injected into the cluster over millions of years. Without this feedback, the universe would look very different. Galaxies would be more massive, star formation would proceed differently, and the large-scale structure of the cosmos would be altered in fundamental ways. In recent years, astronomers have made an intriguing discovery. Intermediate mass black holes, those ranging from hundreds to hundreds of thousands of solar masses, may lurk in dense star clusters called globular clusters. These ancient collections of stars, some nearly as old as the universe itself, orbit in the halos of galaxies. Several globular clusters show evidence of central dark masses, regions where stars move faster than they should unless something massive and invisible occupies the center. If these intermediate mass black holes exist, they might form through the merger of smaller stellar mass black holes that have sunk to the cluster center through dynamical friction, or they might be remnants from the early universe. Their existence would help fill in the evolutionary picture, providing a missing link between stellar mass black holes and the supermassive monsters at galactic centers. The concept of a black hole bomb might sound like science fiction, but it's a real prediction from physics involving rotating black holes and certain theoretical particles. If a particular type of field or particle exists with just the right properties, it could form a cloud around a rotating black hole through a quantum mechanical process called superradiance. This cloud would extract rotational energy from the black hole, growing exponentially until it reached a critical point. The result would be a system that's unstable, potentially releasing the stored energy in a dramatic burst. While we've never observed such a phenomenon, and the existence of the required fields remains uncertain, the theoretical possibility demonstrates how black holes can interact with quantum fields in unexpected ways, and how they serve as laboratories for testing exotic physics that has no parallel anywhere else in nature. Black holes have even influenced our understanding of the early universe's first stars, those primordial giants that formed from pristine hydrogen and helium gas before any heavier elements existed. These population 3 stars, as they're called, may have been far more massive than stars today, perhaps reaching hundreds of times the Sun's mass. When such massive stars died, they would have created correspondingly massive black holes, perhaps tens or even hundreds of solar masses from a single star. Some of these first-generation black holes might still exist today, having grown through subsequent mergers and accretion into the supermassive black holes we observe. Every supermassive black hole we see might contain within it the remnants of those first stars, the pioneers that illuminated the cosmic dark ages and seeded the galaxies with the first black holes. The study of black holes has also revealed unexpected connections to condensed matter physics and the behavior of materials here on Earth. The mathematics describing black hole horizons shares deep similarities with equations describing certain phase transitions and quantum critical points in materials. Researchers have found that concepts developed to understand black hole thermodynamics can sometimes be applied to understanding the behavior of strange metals and other exotic materials. This cross-pollination between astrophysics and condensed matter physics demonstrates the unity of physical laws, patterns and principles that appear in black holes billions of light years away may also manifest in quantum materials in laboratories on Earth. The universe, it seems, uses the same mathematical language at vastly different scales and in wildly different contexts. Rest now in the knowledge that these cosmic architects continue their work, shaping galaxies, launching jets, distorting space-time, and hiding secrets at their centers that humanity is only beginning to uncover. The night is deep, the universe vast, and the mysteries endless, but each question answered brings us closer to understanding the grand design. As we approach the end of our journey through the darkness, let us reflect on some of the most recent discoveries and emerging frontiers in black hole research. In 2022, astronomers unveiled the first image of Sagittarius A star, our own galaxy's supermassive black hole, complementing the earlier image of M87 star. This achievement was even more challenging than imaging M87 star because Sagittarius A star, despite being much closer to us, is also much smaller, about 1,000 times less massive. The gas orbiting it completes a circuit in mere minutes rather than weeks, meaning the black hole's appearance changes rapidly, like trying to photograph a fidgeting child. The team had to develop new techniques to account for this variability, essentially creating thousands of images and combining them to reveal the average structure. The result showed the now familiar ring of light surrounding a dark shadow, but this time it was our own galactic center, humanity's first portrait of the black hole that anchors our cosmic home. These observations of black hole shadows provide something remarkably powerful, a direct way to test the geometry of space-time near the event horizon. The size and shape of the shadow depend on the properties predicted by general relativity. If Einstein's theory is correct, the shadow should be circular and have a specific size relative to the black hole's mass. So far, the observations match the predictions beautifully, but as telescopes become more sensitive and can resolve finer details, we'll be able to test for subtle deviations that might hint at new physics. Perhaps space-time behaves slightly differently than Einstein predicted when gravity becomes truly extreme. Perhaps quantum effects leave an imprint on the event horizon structure. These images are not just pretty pictures, they're precision tests of fundamental physics conducted at nature's ultimate laboratory bench. Black holes have also taught us something profound about the nature of information and memory in the universe. The information paradox we discussed earlier has led to the development of entirely new ways of thinking about space-time itself. Some physicists now believe that space-time might be emergent, that it's not fundamental, but rather arises from more basic quantum information, like how temperature emerges from the motion of molecules. In this view, the fabric of space and time is woven from quantum entanglement, the mysterious connection that can exist between particles regardless of the distance separating them. Black holes, with their event horizons and their mysterious interiors, might be showing us that what we perceive as empty space is actually a complex tapestry of quantum information. These ideas remain speculative and mathematical, but they represent a revolution in how we think about the very nature of reality. The advent of multi-messenger astronomy, combining gravitational waves, electromagnetic radiation, and perhaps eventually neutrinos, has opened new windows on black holes. When LIGO detected gravitational waves from merging black holes, it was revolutionary. But imagine the possibilities when we can observe black holes through multiple channels simultaneously. For instance, if a black hole merger occurred within a gas-rich environment, we might detect both gravitational waves and electromagnetic signatures, gamma rays, X-rays, or optical light from the disrupted material. This has already happened with neutron star mergers, and astronomers eagerly await similar observations of black hole mergers in active environments. Each type of signal carries different information. Gravitational waves tell us about the masses and spins of the merging objects. Electromagnetic radiation reveals the environment and composition of surrounding matter. Together they provide a comprehensive picture impossible to obtain from either alone. Looking forward, next-generation gravitational wave detectors are being planned and built. The Laser Interferometer Space Antenna, or LISA, will be a space-based observatory consisting of 3 spacecraft separated by millions of kilometers, forming a triangle that can detect gravitational waves at lower frequencies than Earth-based detectors can access. LISA will be sensitive to the inspiral and merger of supermassive black holes, events that produce gravitational waves with periods of hours to months, rather than the fractions of a second that LIGO detects. With LISA, we'll be able to hear the cosmic symphony of supermassive black holes merging across the observable universe, detecting these events years before the actual merger occurs, and pinpointing their location in the sky with enough precision to observe them with traditional telescopes. This will allow unprecedented studies of how supermassive black holes grow and how they influence their host galaxies during these cataclysmic events. Black holes may also help us understand one of cosmology's greatest mysteries: the nature of dark energy, the mysterious force causing the universe's expansion to accelerate. Some theoretical models propose exotic connections between black holes and dark energy. For instance, if the cosmological constant, the leading explanation for dark energy, represents the energy of empty space, then black hole interiors might interact with this vacuum energy in unusual ways. Some researchers have even speculated that black holes might be connected to dark energy's origin, or that the universe itself might be the interior of a black hole in a higher dimensional space. These ideas remain highly speculative, existing at the boundary between established physics and creative theoretical exploration, but they illustrate how black holes continue to push us toward new ideas about the cosmos. In the realm of extreme astrophysics, scientists have calculated what would happen if a black hole passed through a star rather than simply capturing it. If a stellar mass black hole plunged directly through the core of a larger star at high speed, it would create a tunnel through the stellar material, leaving a turbulent wake. The star might survive this encounter, at least initially, but it would be dramatically disrupted, potentially triggering unusual nuclear reactions or even causing the star to eventually explode. While such events must be extraordinarily rare, the universe has had billions of years to produce them, and somewhere in the vastness of space, such cosmic collisions have likely occurred. Detecting the aftermath of such events would provide unique insights into both black hole dynamics and stellar structure under extreme conditions. As we near the end of our journey, consider this final reflection. Black holes represent both an ending and a beginning. They are the endpoints of massive stars, the final collapse that occurs when all other forces have been exhausted. Yet they also mark beginnings, the birth of jets that seed galaxies with energy, the creation of gravitational waves that carry information across the cosmos, and the formation of laboratories where nature's most extreme physics plays out. They challenge us to think beyond our everyday experience, to embrace mathematics as a language for describing reality, and to accept that the universe contains phenomena far stranger than our intuition suggests. In studying black holes, we confront the limits of knowledge while simultaneously pushing those limits further outward, bit by bit, discovery by discovery. And so our journey comes full circle. We began with stars, those brilliant beacons whose death throes create black holes. We explored the properties of event horizons and singularities, the warping of space and time, the observation and detection of these invisible objects. We've seen how they shape galaxies, launch jets, emit gravitational waves, and pose deep questions about the nature of information, entropy, and reality itself. Black holes are cosmic enigmas, yes, but they are also cosmic teachers, revealing truths about the universe that no other objects can show us. They remind us that darkness can be as revealing as light, that what we cannot see directly can still be understood, and that the universe, for all its vastness and strangeness, follows laws we can discover and comprehend. As you drift into sleep, let the darkness embrace you. Let your mind wander among the stars, past glowing nebulae and ancient galaxies, toward those quiet places where space-time curves so sharply that it folds in on itself. There, in the deepest night, black holes keep their eternal vigil, patient, powerful, and profound. They have existed for billions of years and will persist for billions more, outlasting galaxies and perhaps even the stars themselves. They are the universe's deepest mystery and its most perfect expression of gravity's power. And now, having traveled with them through these 100 facts, you carry a piece of their story with you, a connection to the cosmos and its infinite wonders. Sleep well, traveler. The universe continues its dance, and the black holes, those architects of infinity, will be waiting when you wake, ready to reveal new secrets, answer new questions, and remind us that wonder never ends.